All right, let's get this thing started. So, let's see here. Let me make sure that I'm actually visible on stream. Yeah, looks like it. Hello. Hello, everyone. So, let's see here. Is there a better way for me to lay this out so I can actually see what's going on? Not really, huh? Not really. Well, we'll just have to make do. So, today's project is going to be laying out a circuit board for the little QRP amplifier that I made over the course of this past weekend, which is this guy. It's a hot mess. It's so delightful. And basically, it's going to be takes a 5-watt HF ham radio signal in one side, goes in, I'll do a better view here. So we're coming in to the input, goes into the input relay there, and I can either bypass it through the coax, through the output relay, or can use these amplifier FETs in the middle to go from about 5 watts in to about 50 watts out. Now, obviously, this was a prototype, and was very hastily made, but it works great. So now I'm going to turn it into a PCB so I can make another one that'd be a little bit more mechanically stable. Let's see how we're doing over here. So we're going to start with, let me bring us back over to Eagle here. Great. So I'm going to start a new project. I don't think you're seeing Eagle. Are you? Yeah, you're seeing Eagle. Okay, great. So let me, I'm going to start a new project. Sure, I will save the library I was working on. Overwrite project file, Eagle, EPF, sure, why not? We're going to call this QRP Amplifier. Great. And then within that, I am going to start a new schematic. There we go. Big empty schematic, just waiting for populating. So what I think I'm going to do, just so you get a sense of what I'm doing, so the basis of this amplifier is this circuit by WA2EBY, which was in QST much more than a decade ago, which is very exciting. So what I'm going to be doing, so I took this circuit and combined it with a couple of other similar circuits. This one from G0KLA, which is very similar. It has the same two IRF 510 FETs as the power source, but a slightly different transformer layout and some switching. And then, of course, Ashar Farhan out of India also did a similar build with one IRF 510 FET. And a different switching arrangement again, and a very different transformer arrangement. It's weird how he's feeding this one. Not weird, but significantly different. But in any case, this was also sort of interesting. I think the most interesting part of a project like this is trying to disentangle which of the pieces of the circuit are critical and which ones are a little bit more flexible. And so looking at sort of the evolution of this design between three designers was kind of interesting in that sense. So this essentially is the circuit that we're going to be laying out. I'm going to, as I go, incorporate the modifications that I made as I went through my process. I'll tell you what, let me move you off of here for a moment. We can do this a little bit more cleanly. No, that's not going to quite do it. Let me see a little bit of how the sausage gets made. But by that, I mean how I'm figuring out how to make the sausage live in real time. All right, so you should see that. Yes? Yes. Okay, so there's our circuit. We'll make Adobe behave a little bit more. Okay, so the first thing, we're going to sort of start from the front end of the circuit here and work our way back toward the power amplifier. So let's start by laying out the RF input circuit and switching relay, and we'll start with this TR switch. So what this circuit here is doing is, so the RF would come in here at 5 watts. We would sample it with this 1 nanofarad cap. We would put it through this voltage divider, so we're, again, sampling just a small piece of the current. We're rectifying it, do a little half-wave rectification with those 2 diodes, and then we're using that to charge up this 1 nanofarad cap. And when that reaches threshold voltage of this NPN transistor, we'll turn this on. When that turns on, it's going to pull this part of the circuit to ground, and that's going to allow current to pass through our switching relay. In this case, this layout would have a single double pole double throw relay. I have a single pole double throw relay. I have 2 relays, each of which is one's on the input, one's on the output. So basically, I'm routing this output to an input relay and an output relay. So there's that. So let's see here. So I'm going to take this circuit. So we'll start by laying out the BNC connector and then the remainder of this circuitry. And we'll see as we go. I did a little looking to see which of the parts I would need were available in advance, but I didn't verify every single one of them, so we may find out we have to build some parts along the way. Let's see if any of these look like the kind of connector I'm hoping to use. None of these panel mount, these surface mount ones are exactly what I want to do. I've done these right angle jack style ones before, just here, they're fine, and they're mechanically robust, but they don't allow for a whole lot of flexibility as far as how you mount a panel mount BNC connector on them. So what I think I'm going to do instead is come down to the pinhead library, which has various header pins. And I think what I'm going to do is actually just drop a pin header on the board and assume that when I wire these up later, I'm going to put a separate BNC jack on the outside of the case and then wire it with a little bit of coax to the PCB. Let's start with that for now, and if I change my line later, I'll come back and change this. So we'll go ahead and drop that in there. We will name it, let's call it RF in, and then I'm going to drop, let's see, actually I can just copy that one. I'll copy that there, and we'll name it, and we'll call it RF in ground. Great. Let's see. Next, let's go back to our schematic here for a second. Okay, so yeah, good. Everything's still showing up. That's very exciting. So I need a 1 nanofarad cap or a 0.001 microfarad cap. I need a 1K resistor and a 4.7K resistor. Okay, so let's go back into our schematic. No, not into our libraries. There we go. So we're going to add. So if memory serves, the generic caps are, a lot of them are in the resistor library. No, maybe they are in the cap library. Let's see, capacitor. Trim capacitor. Yeah, see, this is what I was, there we go. That's our generic capacitors. Yeah, great. So I'm just going to drop in one of these generic C5B5 with a 5mm spacing. That's about right. That's about what I've used. And the nice thing about something like this, because I'm not going to necessarily put together an exact BOM to order with this, I'm going to use parts out of stock. As long as my parts are sort of generically large enough, my footprints are generically large enough to fit the parts I might have in a junk box, then most of the time this will be fine. All right, so let's take that one. We'll drop it in. I'll tell you what, I am actually going to move this RF ground up here out of the way. Put that here, that'll be C1, and we will give it a value of 1 nanofarad. All right, and then I need a Now I need a resistor. Let's see. And any of the resistors in here that have the V suffix typically are the ones that you're intended to mount vertically. So instead of having the resistor horizontally mounted with your PCB underneath it, you mount the body of the resistor vertically, and then you fold one of the top leads over, and that just saves on space on the board. So I think one of these, let's see, one I used last time that I really like the footprint of. Yeah, the 0411V. So again, I'm not being super duper picky about which symbol I'm choosing, because I'm just going to use junk box parts for some of this. So I'm just going to drop in a pretty generic symbol, and if I want to get fancy about it later, I can. So we'll do our 2 resistors there. We're going to value them both. This will be 1K. This will be 4.7K. And I'm going to drop in my ground symbol. There's ground. Drop that in down there. We'll drop that in down there as well. All right, and then let us start wiring some of these puppies up. Ooh, I didn't do that right. Let's see here. I always forget on these header pins. Yeah, so the connection is on the left-hand side there, so that's a little janky, but I think we will survive. Okay, so now, just for the heck of it, I am going to, well, save. Yes, save. Let's call this QRP amp1. And then I'm going to have it auto-generate a board file for me. Let's see here. Oh, it's Kenneth Finnegan. Kenneth Finnegan, welcome to the stream. First me. It's working. Oh, this is such a good sign. Kenneth Finnegan says, can I be a moderator so I can drop links in the chat? Sure. You sure can. I think Kenneth Finnegan is now a moderator of your channel. Well, that seems like a recipe for everything going great. Awesome. Kenneth, I clearly haven't figured out the best layout for me to see all of the things that I want to see at one time, but I'm gonna try. If I put your chat over here, then I can kind of see it. Okay, and then, what else? Oh, I could go over here. Yeah, so, Kenneth, because there's limitless power. It's posting links. Thank you, Kenneth. All right, so let me continue on with the layout. So we did the first part of this layout here. We did the cap, we did the 2 resistors. I'm going to add these 2 1N4148 diodes. Those are small signal switching diodes. And I don't know if there's going to be a symbol for them. Let's find out. 1N4148. If we're lucky? No. Okay. So the question is, are we going to put a generic diode in? Oh, no, wait. What are you talking about? 1N4148. It's right there. Well, either of those should be fine. I'm going to use the smaller version because I have a lot of tiny ones of that. Okay, so we're going to do 1 from ground up and then 1 in series. There is probably some actual PCB layout engineer who's telling me that my methodology for going about all of this is wrong. You know, that I am not doing this correctly. Oh, have I been using the wrong tool this whole time? I hope not. Let's see. Now, why did I not get a junction here? Do I not junction by default? That's strange. I was so sure I would get a junction by default when I did that. All right, so this is part of the reason I wanted to auto-generate a board file, because if I'm not routing this correctly, if I'm not doing this right, it will tell me immediately, because all the parts will have no connections between them. It says board file does not exist. That's good. I want one. Oh, no. So, yeah, so see, here's all my components in a sort of a hot mess. Well, good. Well, that means the wiring is going fine, so we'll come back to that in just a little bit. Okay, so where were we? So, all right, we had our 2 small signal diodes there. Let's do the actual RF sensing part of this circuit. So I've got another 1 nanofarad cap there. I've got a 10 nanofarad cap there. I've got this 2.2 microfarad cap here. And again, so that's a great example. So in the circuit that I actually built, I'm using a 2N4401 for the NPN transistor over here, because it's just what I had, and a 4.7 microfarad cap over here, because again, it's just what I had. So I'm going to drop in some values per this schematic, but I'm also not going to sweat it too much when I actually come to build the thing. Let's see. Okay, so missing a junction between resistor, divider, and diodes. I am. Kenneth, you might actually know. I could have sworn I was going to get automatic junctions when I did this. Is there a way to enable automatic junctions and routing nets that terminate at the end of other nets? Maybe I'm crazy. Well, in any case, so we'll do our 3 caps and our NPN transistor. So let's just keep our symbols consistent. So we'll take our cap there. We'll take our cap there. All right, and we will take our ground symbol here. And I'm going to need an electrolytic capacitor. No, that's not how you spell capacitor. It's going great. Kenneth says, I haven't used Eagle in 5 years. Double click maybe, or start the trace from the junction and end on the component. Okay, worth trying. I can get behind that. All right, let's see. Now, where are my... Yeah, all right, so... Do I really not get any electrolytic caps? Oh, these are bipolar electrolytics. Why do I not get any vertical electrolytic capacitors? You know, the way that everyone mounts them. That's weird. Let's see. I may just not be looking in the right place. So I'll do what I usually do and just go through all the packages it might be. Okay, here we go. Capacitor polarized. Now these are all surface mount, but not all of them. Okay, so there are some options here. Yeah, okay. Well, on this one, I'm going to be just a little bit picky. I am going to actually go and maybe I can do it on the board. I have the little board next to me, and I have my calipers just here. So I'm just going to measure the lead spacing on this example cap that I use, because I find that most of the junk box capacitors I'm using are about this size. So I don't think there's going to be any good-looking way for me to do this on stream, but let's see. All right, let's zero that out. We'll set this to millimeters. This is 5.25 millimeters in diameter, and the lead spacing is, I don't know, 2.6, 2.7 millimeters. Again, junk box. It's not gonna matter. All right, let's see. So this looks plausible. 5 millimeter diameter. Well, that seems plausible. All right, well, let's drop that in. That at least will be close enough. So we'll make sure we're rotated correctly. All right, so let's see. All right, so now let's try the Kenneth figure method. Let's see if this works. If I go from there, no, I still don't get a junction. That's just strange. Well, I mean, I guess it's a feature, right? Like, it's not auto junctioning for me. Maybe I have just been working in Spice too much. Kenneth Finnegan says, terminology clarification: radial capacitors are where both leads come out of the same ends and it stands up. Axial caps are where there's one lead on each end, like a resistor. Ah, okay. So so this electrolytic cap that I'm dropping in will be a radial capacitor. I guess all of these will mostly be radial capacitors, but the resistors that have leads on both ends will be axial components. Good to know. You'll learn something new every day. All right, so let's see. I need to drop in this transistor and then finish wiring up those two nets. So now for the $64,000 question, which version of the 2N3904 am I going to use? So none of these are the versions. So I purchased a bulk bag of these a while back, just because they're a useful NPN transistor to have around, and they are the ones that I purchased. I didn't really look very closely. I just picked a relatively inexpensive option, a DigiKey, but they're not this triangle leads. I can do it on the screen. It's not this style. It's not the style where the 3 leads come straight down. I have the splay lead version, which is just a little bit easier. I find if you think you might have to rework the circuit, or like if you blew up a transistor, the splay leads are just a little bit easier to like get a solder sucker or solder wick onto. I mean, they take a little more space, but we shall see. So Ken suggests 2222. No, I know there's a generic. I think there's a generic NPN transistor set of models. Let's see. Let's span these names out a little bit. These are all... Ooh, there we go. These are closer. So I think this is what I'm looking for. I hope so. I should check that the collector base emitter designations on these, which is that ECB, BEC, all that. I should just double check the order one more time. Like every single time I use an NPN transistor or a little tiny plastic shell transistor, I have to double check because I can never quite convince myself that I remembered what order they go in. So I think these are all. Well, or I could read the chat where Kenneth says you want an EBC footprint. Thanks, Kenneth. Kenneth is kind of like if Google's was a unit of knowing things, in this domain, Kenneth is at least like 400 to 500 milligoogles, right? Like this is just like you saved me a whole Google-roo. So I guess the one thing I'm now just going through to see is all of these look like they would fit the sort of splay leads packaging that I have. I'm just seeing if there was any options that didn't have that, just sort of see what the other package options were. But I think these are all essentially the same. I'm curious now that I'm in here if there is a 3904 package. Oh, here, 2N39. Oh no, it's that same triangle 3904 package. I'm just surprised that there's not. Sometimes they do hide from you if you just do 2N3904. No, same thing. Sometimes they just hide from you when you do a search. 3904. No. Yeah, I think this is probably a strikeout. Yeah, again, same deal. Okay, well, that's fine. I am perfectly happy to put in a incorrectly named NPN transistor into this situation. And I'm going to want... Ooh, sort by description, says Kenneth. Easier to find all the EBC footprints. All right. I will. TS2 EBC. EBC. Ah. Dun, 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 dun. Dun, 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 dun. CBE, EBC. Okay. TU92 EBC. Will you let me just drop? I just drop this in? Yeah, great. Oh, Kenneth says, or, embrace the idea that you pretty much always need to make your components anyways. Yeah, there is that. If it was anything more than a little generic transistor, I could probably get behind that. But for the moment, I'm going to commit the crime of making the name of this part, the part number. All right, so then I need to value this one differently. I think this is a 10 nanofarad, and then this one is by the schematic, it's 2.2 U, but like I say, we're not going to be super precious about that when it comes to it. All right, did we get everything? We got the 2 diodes, we got the 1 nanofarad, we got the 10 nanofarad, we got the 2.2 U, we got the NPN transistor. Great. So now we get to the point of relay control, and I'm actually going to leave that aside for the second until I end up dropping the relays in here. So, although I guess it's about time, because I'm going to need to put my relays in to do the routing into this attenuation. All right. Well, let's see. Well, let's get this wired up real quick. Do that. We'll wire in the top of that. We will tie this transistor to ground. Yep, and I will remember to put junctions everywhere I need them. Okay, so ultimately, this net is my relay control net. When that gets pulled low by this transistor, the relays will be triggered and will switch over to their amplification setting. I want to smash this real quick. So I'm just going to do a little cleanup on this labeling before we move on. Boop, boop. Okay. Okay, so that's the RF sensing part of things. So now, let's go back to our main signal flow, where we're going to deal with, oops, come back, we'll deal with our attenuator and our input transformer. So I'm actually doing something different from this for the input transformer, so actually we'll pull up a slightly different document, and then into our FETs. So just because I'm not entirely sure how I want to lay this out in the PCB, I'm going to move straight ahead to the attenuator section, because on the prototype, I just had 2 of these little relays that I got from Fry's that were generic and cheap, but I don't know that I want to necessarily standardize on those specific relays just because I happen to have them. So to put off making decisions, I'm going to move past that, and we'll make the amplifier. Let's see here. Just see if the stream is still looking good. It does. It's exciting. Or at least YouTube tells me it is, so that's a good sign. Okay, so let us get past the relay switching. Actually, you know what? Yeah, let's get past the relay switching. So according to WA2EBY, whose circuit this is, you want about 1 watt of input to the amplification stage of this circuit. In my experiments, where I took these FETs as installed with a transformer that I wound, I found that about 2.5 watts, 2 to 2.5 watts was required for full power. So I'm going to do the attenuator slightly differently than what this article would imply. Let me actually get up the G0KLA amplifier circuit as well. Open image in new tab. No, I'm just trying to find a clean way to show this. I'll do it off screen so you don't have to look at it. Yeah, there we go. Okay, so get in there. Yeah, so this is G0KLA's adaptation of that previous amplifier design. So you can see, like in broad strokes, it's very similar. We have the RF input circuit here. We have an attenuator. This is what's primarily different. So we have this trifilar transformer that G0KLA is using to drive those 2 FETs, whereas in this we have this bifilar, with a balun basically there, right, that's driving these 2 FETs. I couldn't tell you which is better. Because the design I found first was this trifilar design, I'm basing my transformer windings off of this. Be curious to try this as well and see what happens. I also, so my bias adjustment is actually much more similar to this other design that's just a bias line, which is 5 volts out of a regulator to a trim pot through a resistor, biasing the gate of that FET. Let's see, what was I thinking? Oh yeah, so WA2EBY has this inductor, this choke in there as well. Probably helpful at RF. I don't care about a little bit of power loss going through a 10K resistor. I mean, it seems to work just fine. In fact, the first time I powered a thing on with my little current limited power supply, I thought I had broken something because my current surged to like 500 milliamps immediately as I was turning the thing on. And it turned out I had just turned the bias all the way up to start with instead of all the way down, so the FETs were conducting, and that was not a great experience. So I turned the bias down and then readjusted it once things were working as well. Shooting the dark based on random internet Googling. Kenneth says options, set, misc, auto set junctions. Okay, so maybe this will get our junctions back on. Misc, auto set junction. Auto set junction is on. So it's a good guess, but apparently that's not what we're looking for. So going back to this attenuator real quick. So I want to use mostly a 5-watt transceiver going into this thing, and I want to take it down for this design to like 2.5 watts. So I'm going to put a really simple 3 dB pad in there. And using an online pi attenuator calculator, because the math is not hard, but the internet also exists. The values that I got were 290 ohms in the shunt sections, is what would be here R8 and R10, and 18 ohms as R9 in this series connection. And wanting to drop about 2.5 watts total, I would have guessed, just based on sort of the similar values that are given in this original circuit, probably like a 1 watt resistor in shunt and a 2 watt resistor in series. And I got a little bit lazy, and I wanted to move ahead on this without ordering some 1 watt and 2 watt RF appropriate resistors. So what I did was put a bunch of generic resistors in parallel to make up the power handling, and it seems to be working fine. They are not, as would be most appropriate, like I guess carbon composition, or whatever the most RF appropriate resistor is. But again, I want this to be something that I can make out of essentially junk box parts, or I could send to someone, and other than probably the FETs and the toroids, they should be able to come up with a working version of this out of essentially what they have in their junk box. So what I'm going to do is lay out these attenuators with a bunch of different resistor mounting options, and then for someone who has the appropriate RF appropriate resistors in their junk box, if you're that kind of person, or if you wanted to order them, you could. If you wanted to parallel a bunch of resistors and do it that way, you also could. So we're going to do that. So what I'm going to do is actually make 6 sets of pads for each of what are here, R8, R9, and R10. I don't want to change the color scheme. Keep the current color scheme, Windows. All right, so I guess layout-wise, I am going to put the attenuation section out here, and I know I'm going to have to deal with RF switching at some point, so I'll leave a little bit of room in here, but I am going to copy my generic resistor symbol over here. Just leave a little bit of room. Yeah, okay. Actually, you know what I should do is actually value one of these first. So I'm going to call this R, let's call this R shunt. Because if you were doing, exactly, say 6 of these, I could put a specific value on the board for what they should be, but I'm not. I'm going to sort of allow myself the flexibility of, if I had, if I wanted to do this as a 1 watt shunt resistor and I wanted to do it with some half watt resistors, I could put 2 in parallel. Total resistance wants to be about 290, so that's probably 2 560 ohm half watt resistors in parallel. If all I had on hand was quarter-watt resistors, then I could do 4 or 6 in parallel, sort of based on what's in the box. So in any case, I'm going to leave these just as R shunt, and I'll have to maybe make a PCB note about what that actually means. And just to make life a little better later, I'm going to redo that right there. Okay, so then 1, 2, 3, 4, 5, 6. Okay, and then no. Group, right, control, right click. I don't know who comes up with the keyboard shortcuts for Eagle, but they're not. I don't find them that intuitive, but maybe that's just me. Okay, so I'm gonna need 2 sets of these. And presumably, I don't really have a problem naming them R shunt. One set of them is on the input side of the pi attenuator, the other's on the output side. I don't know. We're going to have to deal with that at some point. But hopefully in the PCB layout, they'll be sort of separated so we can make that clear. If they're not, maybe we'll come back and relabel them so it's clear that they're 2 separate sets of resistors. Let's see. Kenneth Finnegan says, my preferred way to document this optionally split up the resistance model for boards is to set the total resistance on one resistor, then tag the rest do not populate. Then it's up to the end user to shuffle parts to end up with what the schematic says. Oh, that's quite clever. So the schematic tells you have a resistor of this value, and also I've put pads here and you can fix it on your own. That's not a bad way to do it. It's not a bad way at all. So in that case, this would be, this would be 290, and the rest of these would be do not populate. Okay, yeah, I can get behind that. Let's, this is the way that standard practices in amateur PCB layout happen. Somebody says, this might be a good idea, and some other guy goes, yeah, I can get behind that. Let's see, 4, 5, and 6. Okay. I'm sure, again, there are people who actually lay out PCBs who are screaming because there's some more efficient way to do this, but for the time being, that'll get us through. Okay, so that's our 290 ohms, and then we have 18 ohms in series. So I guess I can just do this again. We can just copy. I hope this is right. No, not quite. Well, that's fine. I'm just going to relabel which is which. Actually, I wonder if it would be more clear. I'm going to put the valued ones right here in the middle so that they're all next to each other. So that if somebody is looking at this, they can see this little pi attenuator right in the center here, and then they might go, oh, I have all this extra room to play around with. We'll just move this a little bit closer. Let's see. Kenneth Finnegan says, we use it in professional board layout all the time because we can change bombs way faster than spinning new FR4, so we add extra footprints as possible to get out of jail options. Yeah, Kenneth, I forgot that PCB layout and module layout is sort of part of your day job. Kenneth, what do you use? I mean, I know you're not using Autodesk's free version of Eagle to do your PCB layout. What is your PCB layout of choice for your software these days? Okay, so we'll start tagging these attenuators in here. We'll go to there. We'll start tagging these in down here. We'll go up one side. We'll go down the other. Great. Okay, and I know I haven't connected my RF signal over here yet because in between my RF input here, RF in, and here, I'm going to have to do my relay switching, my bypass option switching. But again, I'm going to put off making any decisions about the the relay choice at this point because I can. Okay, so from this point forward, so I have my attenuator, and I'm going to have my trifilar toroid here, and it's going to have a center tap and two 100 ohm resistors to ground from. So the center tap's going to be grounded, and then each the phase is going to be grounded through a 100 ohm resistor. So let's put that together. Let's see. Kenneth says OrCAD for schematic capture, Altium for board layout, and I practically never drive it myself because I have my designers do all the CAD for me. So I take similar schematics, redline them, and send it to the designer to do the whole board design for me. That's quite nice. Yeah. So so you're doing sort of the design level things, and then as far as like schematic capture and actual layout, you got people to do that, which is quite clever. Well, given them, so my people is me, so I'm gonna chug along. But it's always nice to have people to do these things. Just gonna do a little quick and make sure the stream still thinks it's healthy. It does. It still does. This, I gotta say, this was relatively painless to set up, which was so delightful. Okay, so trifilar toroid. Let's just drop that in first and get it situated. So thankfully, there is a really nice toroids library. But really nice. It's not huge. No, other way. It's not huge, but it has lots of the common amateur applicable toroids that I might want. Where is it, though? It's just called toroid. No. I need to open up the appropriate Eagle library and make sure that I'm actually Eagle lib. Oh, this is just for opening anything. So actually, I think I'm going to have to go back to my control panel and just verify that I actually do have. Yeah, so I have this. Oh, I need to. Yeah, that's right. I have to activate it. That gets me every time. So you have to you add this library. When you add the library into your file, your .lbr folder for Eagle, it automatically drops it in here, but it doesn't activate it or whatever it calls this. Use. It doesn't say you're using it by default. Well, I'm using it now. So, all right. So now, in theory, if I go back into add parts, I will. Oh, it's over here now. Yeah, there we go. So, in fact, I want to see toroid, the library. So, what does G0KLA recommend? G0KLA recommended first transformer, 12 trifilar turns on FT50-43. That seems reasonable. So I have a trifilar toroid on an FT50 if I'm lucky. Trifilar transformer on a T50. Oh, what a gem. So, all right, we're going to drop one of those in. In fact, I'm going to start a new, so I'm going to assume that my relay switching section goes here, my attenuator, which got so huge over here. So just for layout sake, I'm going to start all the way down over here with my transformer section. I am going to bring my signal line down and I am going to ground the other side of this winding. Personally, I like it's a little bit of a brain shift, but Eagle, like so much of the other what is now Autodesk software, is ultimately command line based. So I find it faster to type in the commands and then implement them rather than usually clicking them over here. For some reason I click on add typically instead of typing add, but everything else I like to type in. At work we use primarily Autodesk's AutoCAD software when we're working with physical designs, but when we're doing lighting models, we use a different product called Vectorworks from Nemetschek out of Germany, just because its built-in lighting libraries are so good. And that one is not at all command line based. Everything, almost everything, is click to operate, and so going back and forth between the two is just a little bit strange. But what can you do? So type in ground. So the center tap of this is grounded. Is this what I mean to do? Let me take a quick peekaroo. So let's see. This side of the L2 winding and the other side of the L3 winding are both grounded, which I think is what I'm about to do here. Yeah, okay. So we'll do that, and we will do that, and I will junction them. Very good. All right. Oh, and then I need, let's make this a little bit clearer. Let's move this out. And, yes, that'll be ground. And then I need a resistor from each of these windings to ground as well. That is 100 ohms. So all right, so I have a choice to make here. So I find this piece of layout for this transformer, it's pretty, and it shows off the symmetry of this transformer, right? The center tap is grounded. This winding is grounded through 100 ohms. This winding is grounded through 100 ohms. We're both going through 100 nanofarad cat. Like the symmetry of all of this is very nice because it emphasizes the sort of push-pull nature of the design. But I think, well, it's a PCB layout. It doesn't really matter. What I was going to say is, grokking this for the first time, I think it's easier to understand if these resistors had been grounded to separate ground nodes, just to emphasize it's not that it's important that these 100 ohm resistors are connected to the center tap. They're just to ground, and we just reuse this ground symbol. So as neat as that is, I think it would be an easier design to understand if these were just flipped around, so you had 3 ground symbols and just emphasizing this is 100 ohms to ground. In any case. It's my schematic layout, so I can do what I want, and I will. So I can take one of my standard resistor shapes. Oh yeah, cool. So I'm going to, what I'd like to do is have ground coming down. So I think what I'm going to do is I'm going to undo something I did a moment ago and move this ground closer here. Just so that's, yeah, there we go. Look at that symmetry. Yeah, cool. All right, so then, oops. Then I'm going to add my resistors to ground here, and I'm going to do them separately because I can, because it's my PCB. I'll do what I wish. All right. We'll wire those up. We'll wire those up. We'll wire these up. I think, oops, just for clarity, I'm going to try not to have any wires that just pass through the end of a component if they're going to join it, just so it's super clear that there is a bit of wire there making the connection. That's I'm sure not necessary, but I'm going to do it anyway. So these are 100 ohms a piece. All right, and there is that transformer. Great. So let me just take a real quick peek. All still seems good over in YouTubesville. Great. All right, so now what comes after this transformer? We've got a 100 nanofarad cap that leads to the gate of these IRF 510s. And then there's some bias circuitry that we'll have to deal with. So let us find our IRF 510s. So I'm pretty sure that there is an IRF 510 symbol already in here, but it's laying down. All right, so this is going to be a design decision point. So in the prototype, the heat sinks are, sorry about that, are giant. and they're kind of just flapping around in space. They're not actually attached to anything because I didn't do a great job of thinking about heat sinking when I was first laying the thing out. I had some little tiny TO220 heat sinks, and then I started thinking about how much power these things might actually dissipate, and I got scared, and I threw these things on here. But they make it kind of a mess. So because this is, in theory, a project that someone should be able to put together out of their junk box, we have a couple of options as far as heat sinking goes. We could either assume that the user is going to have a couple of, small but hardy, discrete heat sinks for a TO220 that they are going to use, one heatsink on one heatsink on the other. The other possible assumption is that somebody has a leftover big chunky heatsink from an old PC or an old project, a CPU cooler type of thing. And this is what made me think of it, is I have several of those that I've picked up at ham sets, like $1 for a block of aluminum that big, that I use for like LED lighting projects. But the layout for those two options might be different. So I think, need to make both an option or pick one and commit to it. And the difference for me would be if I'm going to use one of those big blocks of aluminum, that I would probably put the two transistors vertically and right at the edge of the board. So you mount it next to your heatsink and you have your heatsink hanging off the side, sort of like that. Or if I'm going to assume they're going to be discrete, then I would put them on opposite sides of the board, say, so you could hang one heatsink off one side and one heatsink off the other. I know the eBay, like the mini PA amplifiers, what they do is actually have the whole PCB mounted, if you will, on top of a heatsink, sort of like that. And then they have a cutout right in the middle of the PCB for the tab of the TO220s to hang down through, and then you sort of bend them down and they sit just right on that heatsink layer there, which is very clever. I just don't know if that's what I want to necessarily commit to in this design. But for the sake of progress, and the other thing about that sort of design is you have to have the inside of your PCB routed out, and I'm not 100% sure if I want to rely on people having the access to a PCB house that's going to do that kind of internal routing. I guess I could, or say, punch it out yourself, but it seems like an extra sort of layer of something to have to rely on. For the time being, just for the sake of laying things out, I'm just going to throw in this IRF510 symbol that I have, get the circuit laid out, start laying out the circuit board, and then think about what my options are. We could do a couple different sets of pads for various options if there's a way that makes sense. But I think let's just get the circuit on board for now. So we'll do 2 IRF510s. I'm going to move this wire up just a little bit so we have some more room to work. And I'm going to move this down so we have a little more room for bias circuitry. And I need a 100 nanofarad cap, which you don't have yet, but that's fine. So one there and one there. And this is 100 nano and 100 nano. Oops, 100 nano. Let me open this back up. Gotcha. Let me just see here. Great. Okay, so let's get that wired. We got that wired. Got that wired. We got that wired. Okay. And then I'm going to do my bias circuitry in the middle here, which is just the 12-volt input option to this to the amplifier. It goes into a 7805 through a couple of Trimpots, which are well bypassed, and then into each of these signal lines, the FETs. So I'm surely sure there is a 7805 part in here. No, but I would be wrong. Let's see. Well, dang. I have used a 7805 in other projects. I think I've been... Oh, it's a generic. That's why. 78. There we go. I want the vertical version. 78 double XS. That looks like the right package. In, out, ground. Yeah, I believe that's correct. All right, so let's do this off to the side somewhere. We're just going to establish a little bit about the power routing for ourselves right now. Let us add an extra header pin that will represent, for the time being, our plus 12 volt input, which is under pin head. We'll do, let's see. I'm going to do these as separate 1x1 headers because I want to space them out a little bit, because I want to have the option. It's a little easier to tack in like number 20 wire if they're not adjacent pads, I think. But we can always change our mind later. All right, so we're going to wire this to that. We're going to name this, let's name this header 12 volt in, and we're going to name this net plus, let's see, do a $ plus 12 volts. I think that's right. Okay, and then the regulator needs to be grounded. Great. And then I need a 5 volt net coming out of this. 75, and then I need to name this 5 volts. Okay, and now can I label this? Yeah, great. So I'm going to label this as 5 volts. And now's where I think that is true. I'm not 100% sure. I think that is an appropriate way to denote that. It's not great, is it? that wiring. But oh well. Let's see. Ken says, can probably get away with a 78 LO5 for bias. Depends if you want it in a TO220 or a TO92 package. Yeah, that's fair. I happen to have a bunch of TO220 packaged ones from another project. So I'm going to lay it out with a TO220 because you can squidge the TO92 packages into the holes for a TO220 if you really try, I think. I'm going to try. All right, so now I'm going to need a couple of Trimpots, which of course are not under Trimpots. I think they're under the resistor library. No? Let's see. Resistor, shunt, power, pot. Trimpot US. Okay. So again, let me take a little squiz at what I found here. I'm going to choose a Trimpot model that has some spacing between the leads, but not too much, just because, again, that's going to make it easier to use more junk boxy kinds of parts. But the parts that I used happen to have... See, this is the problem with these giant added-on heatsinks, is now I can't... to get at anything, I have to basically take the heatsinks off. You can see... I don't know if you can see. Let me find out if you can see. Yeah, so right down, let's see, where are we? Yeah, so those bodges of resistors there are part of my input pi network. And to get those in, I had to take off like 4 wires and both of the heat sinks and like untach some things from the resistor. It was just a mess. So that was part of the impetus for laying this out on a PCB. Let's assume that our Trimpots are going to be... Let's see, a lot of the ones that I happen to have in stock, I guess I'm just making a value judgment now, are the ones that lie down but have 3 contacts that are collinear. It's none of these Panasonic ones. Let's see, it's something like that. 0.1 millimeter, that's a decent guess. Oops. What? Come back. No? Oh, no, didn't get to add that part. Well, that's a shame. I want to go back to pot. Go back to Trimpot US. Where's my Trimpot? There we go. Yeah, all right. So I'm going to, let's see, let's go this away. Try and do this in a bit of something of a clever way that's not confusing, but also lets me duplicate this for the top section. So let's do one right there. We will insert our ground symbol. We will duplicate our resistor here and our bypass capacitor there. And this will need to be grounded. Okay, so those get wired, those get wired, those get wired, those get wired with a junction. And that gets wired. And then if I name this the same as the other junction, yes, I would like to make those exactly the same net. And then I would like to label that plus 5 volts. And then I will add a little circle there. Make 5 volts. I'm sure there is a cleaner way to do that. Like there just must be. But for the time being. Ooh, I am missing some other junctions. We're going to have to do a junction check when this is all said and done. I'm missing one there. Man, what is happening? Let's see. Ken says, you do still need stability bypass caps on both pins of 7805. TI recommends 0.33 on the input, 0.1 on the output. I usually use something like 10 micros on the input, 1 micro on the output. Yeah, that's fair. I should go drop those in now. I typically do, and if memory serves, those are between, or just from the input and ground. So I will have a bunch of bypassing on this 12 volt input line and this 5 volt output line, but it's actually not a crazy idea just to put those right here in the sort of power section of this layout, just to remember that those should be located close to that regulator. So let's do that. Let's do another small electrolytic cap there, and we'll assume we have a small, I'm probably going to do like 100 nanos on the output. Yeah, okay, so we'll get those wired in, we'll get that wired in, we'll get them junctioned, boop, boop, and we'll get the, oops, no, sorry, we'll get them grounded just there. Okay, cool. Thank you, Kenneth. A little quick save. Let me take a quick look at that. Okay, so all right, so I've done bias on the gate, one gate of IRF 510 here. I'm going to need bias on the other one. Okay, so if I've laid this out nicely, I should be able to just copy. Oh, it's so big. I really would like those to be the same. For clarity's sake, well, maybe I can condense this layout just a little bit. I suspect I can. So if this were there, and that were there, and that were there, that buys me like 1 grid space, so that's not really gonna cut it. I suppose I could do that. Here, let's. I'm so sorry, future humans. I'm just gonna condense this even more. Oops. Junction. Yes. All right. So now, what I should have done is built this in the more confined space, because then it would definitely have fit in the less confined space. Well, that's not super clear. I just like, see, having the ground symbols at the bottom is just so much more clear than anything else. Well, I guess I can do that. Yeah, so that's a little bit more compact. Let's see. So that moves up. That moves up. That moves up. And then the whole thing moves over. Well, that's still pretty clear if you know what you're looking at. I think that's... Well, let's see. I hope that's fine. Let's select. We will copy. Yeah. Yeah, all right. Well, that's not... It's a little bit cluttered. I'm not a huge fan, but I think that will work out just fine for now. All right, so we've got... And that'll have the junctions... No, I need... I see, this is what is just a little bit confusing. I think I need a junction there. I'm pretty sure I do. I can't hurt to have a junction there. Okay, so we've got our bias sections. We've got our DC blocking caps. We have our FETs. So now we're going to do the 2 output transformers. So for the prototype, my transformer here was exactly as G0KLA did it, which is bifilar turns on a pair of FT3743s. And then, because of the time I didn't have this Material 43 Amidon binocular core, I used a pair of smaller binocular cores. I'm not sure if you're going to be able to see them there. Yeah, so you can just see at the top of the PCB there. So that is a pair of BN202 cores, BN43202s, which are quite a bit smaller than a 7051 core. But part of what gave me some confidence in looking at that was looking at VU2 ESE's version of this design. Not exactly the same version because his isn't a push-pull, but his final sort of impedance transformer was just a single FT3743 with 22 gauge wire. So I'm still learning about how you adequately size your toroidal transformers for the amount of power you want to put through them. There's a really good mini article / website that I found in the process of learning about this that I've made it quite clear, and I understood it when I read it, and then I looked away and I didn't understand it again. So clearly it's a learning opportunity. But I'm sorry for just Googling things on stream, but let me just see if I can find that because it was just so very good. Let's see. Toroids. I'll give myself 30 seconds to find this. And if I can't, then I will just deal. But it was just living on my phone for so long. And it was just such quite a good answer. Now, I'll have to find it at some other point. But in any case, sort of empirically, the 2 BN43202s will have about a half of the A sub L value, the impedance value, that is per turn squared, that a BN43 7051 would have. So far seems to be fine. I haven't gone as far as to try and measure the output impedance of this circuit. Seems to be working just fine. I haven't blown anything up. It's putting out power. And the low-pass filters, which will come later, will do a little bit of the impedance matching for me. So in any case, hand wavy, it all seems to be going fine. So let's drop these 2 transformers in the schematic. So I need a bifilar transformer on a size 37 core. Let us see if our toroid library will help us out. Toroids. 37. Auto transformer, no. Tapped transformer, no. Transformer, T37 transformer. Yes, very good. Thank you, Toroids library. You're saving the day. Okay, so there is my transformer. Let's move that over just a little bit. Let me see here. Okay, so now the alternate side of the transformer are linked to the drain of their respective FETs. and the other side is tied to our power rail. So you'll notice on this design the power rail is plus 28 volts, so I'm actually going to create a separate net called power, because in this design I've given myself the option to power the drains of these FETs here either from my 12 volt rail or from an alternative power source. So I'm going to make a power net there and tie these into that. So, oops, come back, Eagle. Where'd you go? Eagle. So let's just bring these out here, bring that out there. All right, so let's, you know what, just to make ourselves easier. So G0KLA chose the top of this side of the transformer to touch the top FET. So I'm just going to copy him just because that's what we do. And that means that this side of this transformer will attach to that FET. I'm going to junction them appropriately, and then both of those will attach to the power rail over here. And I'm going to call this, I'm just going to call this power. Yeah, great. And it needs to be pretty well bypassed, so let's assume, let's see, in my current design, what am I bypassing with? I am bypassing with another 4.7 microfarad cap and 100 nanofarad cap in parallel. So that's not an awful combination. All right, so it probably wants to be even better bypassed than that, but there will be other bypassing of feeds into this part of the power system and other parts of the circuitry, like where the 12 volt line comes into the back of the radio. There is a bypass cap. There's a bypass cap on the same line, but near the 7805. There's bypass caps here. There's bypass caps on the switching mechanism that switches in the alternative power supply. So not to say that there shouldn't be more bypassing right here, but and then we're going to junction those up. Boop, boop. Oh, and junction there. Boop. And then I'm going to label this power net. And then add a small circle. Yes. So that's my power net. So there's that. And wow, I really should have made the monitor I'm streaming from not my primary monitor, so when I alt-tab between all these things, you're not just looking at my alt-tab display. And you learn something new every day. Let's see here. All right, so now for the output transformer, which is another bifilar transformer on my binocular core of choice. And I think what I'm going to do is lay this out as if it's a BN437051, sort of as described here. Or let's see, what did WA2EBY use for transformer 3? BN433312. Yeah, so you know both of these authors have used this 43 material for a ferrite toroid, but size is not super critical. The 7051 is a pretty chunky one, so I think I'm going to lay it out with the chunkier binocular core, and then once again people can have the option of substituting with something else. You could even stack up a bunch of 3743s or 5043s to make that transformer. I don't know what that would look like, but you could do the math. So now I would be almost certain that I don't have a BN437051 block in here. Yeah, I can't imagine. So we might actually have to make a component. Won't that be exciting? Okay, yeah, no dice. All right, so let's just commit ourselves to making one. And I actually, since making the original prototype, I actually bought a couple of 7051s on the slow boat to have on hand for exactly such an occasion. So let me see. I'm sure our favorite website. Yeah, so toroids.info has our favorite our favorite toroids information website. Has data on that particular multi-aperture core. So we can use that to make our symbol. All right, so let us open up my library of parts. Now, I think I'm going to just add this to my Scratch library because I don't think I want to muddy up what are my transformers and what is this sort of generics toroids library in case I end up recommending it to somebody else. It's not going to be entirely clear what comes along with it and what was just something that I added. So let's open up jglib. And with this open, I am going to go to my toroids library. And find so I'm going to reuse this symbol for my transformer as well, but not this package. So I'm just going to, let's see, can I just, oh no, copy to library is what I want. Yeah, so now that's slurped in that entire device, the package and the symbol, so I can reuse that. So I'm going to need a new package. It's going to be a BN 7051 pack. This is just a thing I do to keep things straight. If I'm creating a one-off package, I'll name it pack so that the package and the device don't have the same name. It just helps keep it just a little bit clearer for me which is which when I'm assembling an Eagle. All right, so new package. Yeah, great. All right, so let's go back to our toroids.info. Okay, so the let's call it the vertical dimension here is 28.7 millimeters, and the horizontal dimension is 28.7 millimeters. Oh, that's easy. So let's go back in here. Let me just double check that my grid settings are what I want them to be. Let's see, 0.5 and 0.025. Is that going to be sufficient? 0.5, 0.025. No, I'm going to go to a 0.01 secondary grid, alternate grid, I guess you'd call it. Yeah, okay. So starting from the origin, I will come down here. So let's go up here to make math a little easier. So we said that was, we'll do it in inches, 1.13 inches per side. Great. And I'm going to just now outline that with lines, and then I'm going to delete that rectangle. Great. So that is the footprint of the core itself exactly as it is sized. So now I think I'll add a couple of marks just to indicate orientation. So the center-to-center spacing of the holes in this core is the E dimension. It's 0.55, so that's what, 0.275 inches from center line, which is, if the whole thing is 1.13 inches across, means that center line is at 0.6. I'm too old to do math anymore. Okay, so the whole thing is 1.13 inches across, which makes me think that the center line distance is at 5.515. Let's call it 5.515, yeah. And then the distance from center line to either of the holes is 0.275. You subtract those two, and the let's see, 0.515 minus 0.525 is 1. This is doing math live on stream. It's very exciting. Let's see, 510 is 4. 440 is 240, 0.24 away from center line. Does that seem right? 0.240. Add those back up. 0.24, yeah, 0.515. Okay, and then so from the bottom, we have 0.515 minus 0.24, which is 0.35, which is 0.2.75 from the bottom. Is that right? Oh no, it is yeah. So it's 0.24 inches from the bottom of the toroid. Well, I'm sure that was stimulating out there. I'm sure it's loving. Oh man, Kenneth Finnegan dropping ferrite links into the chat. Toroids and info, BN43 said, yeah, Toroids and info is great. If you ever go into the deep end of ferrite, tend not to trust Toroids and info. They paint specs with a broad brush, and you want to rely on vendor specs. Amidon's actual spec for 43 material. Permeability isn't all just one number, but it's a function of frequency. So toroid.info's single numbers for specs is a bit simplistic, but good enough for HFs. Yeah, it's a fair point. If you haven't noticed the hand-waviness of my HF level design and the casualness with which I will gladly route RF over bits of wire, there's a lot of things you can get away with when doing an HF amplifier that you couldn't at VHF or UHF. But just for the sake of thoroughness, let's take a quick peek at this actual Amidon data sheet. Yeah, wow. So here's permeability as a function of frequency for the number 43 material. Permeability versus temperature, change of impedance versus temperature. Interesting. Yeah, so you can see that for a ferrite that you're using, what I'm learning from this is that for a ferrite that I'm using essentially as a transformer, the change in impedance, the change in, I guess, in permeability between, say, 1 megahertz and 10 megahertz and 30 megahertz there is significantly less than an order of magnitude, which is good. That's kind of what I would like. It's probably a factor of 2 or 3, and for a transformer that just needs a brunt impedance, and I don't think I'm riding the sort of bleeding edge of how much impedance is appropriate for that transformer. I think I should be okay. But Kenneth has linked this in the chat for those who want to take a look at it from Amidon. Okay, so back to math on stream. So I'm going to put a line here at 0.24 from that end, and then the spacing of those is 0.55 plus 0.24 is 0.79 inches. This doesn't seem right. What have I done wrong? Snap. What's happening? So center line we said is at 0.515. That we know. Is that also wrong? Did I also do a bad math? According to my math, this just doesn't seem... No, it should be 0.558. That's what's gone wrong for center line. This is the only time I wish I could do this in a proper CAD program, that I could just say, please be at the center point of this point, and then give me that dimension. But there you go. Yeah, that'll be fine. So center line is 0.558. The distance between the center lines is 0.275. So let's see. Let's draw in our center line of our symbol here at 0.55. Yeah, so that's essentially center line. So that seems much more plausible. And then accounting for spacing on either side of them. Can this mirror is not like mirror in a drafting program, sadly, I don't think. Let's see. Oh, you know what? Screw it. I could do math on stream all day, but I'm not going to. 0.283. So this should really be at 0.28, and then we are going to all right, copy that, move that up here. Okay, math on stream, all done. So those are the center lines of the two apertures in the toroid, and that's as much as I'm going to indicate, because that's going to give us some leads as to where we're going to put the through-hole pads for attaching the wires that have come out of these things. So let's give ourselves like a couple of tenths. Let's make these fairly large. What is the diameter of number 20 magnet wire? Bueller? Number 20 magnet wire. Somebody give me... I guess I could grab a piece and measure it. That might be... because that would tell me what the diameter of my magnet wire is. My magnet wire... claims to be 0.75 millimeters, which is not useful. What I would like is, in inches please, is 0.031 inches. So let's set this to, I have a 0.03 option here. Let's go 0.035. Let's go a little bit bigger. And we will, I'm going to leave these 2/10, 3/10. So what I found is in winding these toroids, especially if you're doing sort of bifilar windings on these binocular cores, is that having some slop out here, if your toroid winding isn't perfect, is really easy to do. So I'm actually going to move these holes just a little bit away from the end of the toroid here. What I do for 1, 2, 3, 4. Yeah, so 1, 2, 3. Let's see, we do 1, 2, 3, 4. Cheat that back, and we'll do 1, 2, 3, 4. Cheat that back. Great. All right, let's save that. And actually, I guess I should give this a... All right, so let us take a look at, let's make a new device. We're going to call this BN43 7051. Yes, create new device. It is going to have the T50 transformer symbol right there. It is going to have that package. Now, does this not have connections on it? Oh, it does. Oh, great. Now, I want to take a quick look at this symbol and make sure I'm matching up the symbols correctly. Oh, Kenneth has more to say. Oh, very good. I had to figure out a better system so that I make sure I keep your chat window always on top. I wonder if that's a thing. Let's see. Oh, going back to that Amadon dash 8, U double prime is related to the loss near ferrite. U prime is more important for the actual inductance. Good to know the material tolerance is like plus or minus 20%. So build to build matching without hand tuning is poor. Because it says 20 AWG is 32 thou. Guess says this is when we want a real CAD program with geometric constraints. I know. I would take anything. I would take any CAD program. I would take Vectorworks number 8 from 2003. I would take Fusion 180. I would take anything. All right, let us take a quick look at the transformer symbol and what these are. So make sure I have these pins correct. So A and B, we go A, B, C2A, C2B. Okay, so let's go back to our device. Oh, I should actually go back into my package and name. Fusion 180 is half of Fusion 360. Yeah. Now, if you pay quite a bit of money, you can get Fusion 540. but that's just an intern who comes and does half your drafting for you. All right, let us name this to match our symbol. P1A, P1B, P2A, and P2B. Okay, back to the device. Add a new package. No, package is there. Let's connect. So C2A, P1A, 1B, 2A, 2B. Okay. Great. All right, so that should be fine. I guess I could enter a description. Couldn't hurt. A bifilar transformer wound on a BN437041 binocular core. Okay. So now we're finally ready to come back in and integrate that into our design. For those who are just joining us, we are laying out a PCB for a QRP amplifier, 5 watts in, 50 watts out, based on this circuit and based on this prototype, so that it's a little less of a Frankenstein's monster than this. So we just finished making a device, which was the package of the transformer that we are going to use for this project. Now we're going to back in and drop it into the layout itself. So go back down to my, did I remember to add JGlib? Oh, I have a JGlib and I have a JG parts. Well, that's not going to get confusing at all. Let's go back over here. JGlib. Yeah, and use, great. Okay, so let's finally come back in here. So I can add, go to JGlib, transformer, okay. Yeah, there we go, okay. So I'm gonna drop my transformer in here, and I'm going to name it, actually I'm gonna name this T3. I'm just gonna match the toroid, the transformer naming convention to the G0KLA schematic. Ooh, T1 already exists. What? Oh, this was T1. Oh, it's transformer 1. Well, that's fine. We can use U as a designator. That's fine. All right, and let's just verify our windings here. So go into both sides of the primary winding, and the secondary winding, one side is grounded, the other side goes straight to the RF output. Great, we can do that. So we are going to wire this up. We're going to wire that up. Oh, we're so close. We're going to ground this side of the transformer. And then similarly on the output, I think at this point I'm going to do another single wire header point for output, which I might so that on the prototype currently doesn't have any kind of a low pass filter on the output. So I'm thinking that this revision of the amplifier might not have a low pass filter built in as well, but so I think at this point we're just going to do a single pin header, but I can always come back and integrate a low pass filter or two on here. But I think I want to do the in-person prototype of it before I start laying it out in CAD. In Eagle. We're going to name this RF out. Let's see. What have I missed? So obviously we still have relay switching to take care of. And I need to, let's see, while I'm thinking of it, let us add a matching ground point for whatever my 12-volt input is. So on my prototype board, that's just a little power pole jumper with the ground lead soldered directly to the copper there, and then the plus 12 goes over to that switch. Ooh, now might be an interesting time to think about the switching for the power to the FETs. Well, here, let's finish this first. Let's make this a ground point. We'll make this, name it ground. We will tie it to ground, so we have a place to tie in ground from our battery or power supply or what have you. Okay, so just to recap, here's the circuit. So RF would come in here, pass through this DC blocking cap to this RF sensing section, which is going to turn our amplifier on and off. So this RF sensing section, which in fact, let's just label this. Boom. We go through our voltage divider, we rectify, we use that voltage to drive this little NPN transistor, which pulls this low. This is going to be the control net which pulls power through our switching relays, which is a section I have not laid out yet. But when RF was sensed, we'd activate a relay to route our power through this. This is going to be a 3 dB pad, which is 2 shunt 290 ohm resistors and an 18 ohm resistor in series, and then a bunch of other pads in case you wanted to do this as a parallel combination of resistors instead of a single set of resistors that do not populate a destination there thanks to KWF. Then that signal goes down here through this trifilar transformer, which passes right along through these DC blocking caps again, which prevent this bias voltage from getting into any part of our transformer. That bias voltage, we'll take a quick peek, is provided by a 7805. So that RF signal, now with bias on it, powers the gates of these IRF 510s in a push-pull configuration. We pass power into those drain lines via this transformer from our power line. Our power line is not necessarily the same as our plus 12 volt line, and we'll get to that soon. And then those pass through this output transformer, which is that BN 437041 block that we just laid out. And then that goes to our RF output. Oof! Pretty cool. So, what do we need to establish now? We need to do relay switching. I should probably tackle that pretty soon. And we should see if we want to, we should probably deal with the alternate power arrangement. So, really all this alternate power arrangement is the... there is a power switch on the back of the prototype. In fact, I can just show you this. I have the physical unit right here. So, primary power input plus 12 or 13 volts nominal goes through this switch right here. When you switch it on, you provide 12 volts to everything on the circuit. So that's powering the 12 volts for the relays, 12 volts going into the 7805 for bias circuitry, I think it's essentially it. Oh, and power to the drains of the FETs. Now, there's also a tap line coming off of that plus 12 volts here, which is the power line for the FETs passing through this second switch. And when you flip that, you put this plus 13.8 volt source, say, and this plus 13.8 volt source in series, and that becomes the power input just to the drains of the FET, so just to power the unit. So the relays still get 12 volts, the 7805 still gets 12 volts, but the FETs get the output from those two series sources. And that's just to provide some like multiple options, because ultimately I'd love this to be a unit I could take portable. So if I wanted to take a single 13.8 volt battery on a given day, I could, and I would run off of the single 13.8 volt source. And as I saw in the video yesterday, that's about 15 watts of output from a 5 watt drive, which is pretty good. And then with two of those sources in series, so like 26, 27 volts, we get up to 50 or 60 watts. Now, both of those figures are without a low pass filter, so probably the reality is they're a little bit less power than that on the frequency of interest, but that's sort of the order of magnitude of what we're looking at as far as power. So let's tackle that just now in our power section. So I think I'm going to actually just rearrange this to get the ground out of the way. So let's add a switch. So I'm going to put these in the schematic. And I actually don't know if there's a great way for me to well, I'm of two minds about this, because ultimately these aren't going to be reflected in the actual PCB layout, because much like the prototype, these switches are going to be panel mount devices. So really what I need is pin headers and an indication of where to wire the individual switches into the board. I'm not going to do a PCB mounted switch for any of these, because I want to have the flexibility of mounting those switches to the facing of an external enclosure. So here is what I'm going to do. I need a set of pin headers. All right, so we will add, those live in our pinhead library. I want a 1x2, so this is going to represent our primary power switch, just a single pole, single throw, on-off switch, and on-off, which interrupts the positive side of the first 13.8 volt source. So I am going to wire that in place like so. Great. So that represents our power switch. So when the switch bridges those two, power is on. When it does not, power is off. Piece of cake. Let's give that a name. Let's call this switch 1, and we'll value it power. All right. And then for the secondary switch, for the series switch, I need a double pole, double throw switch, which means I have, which means I have 6 contacts. I have 6 contacts. So I think the way I'm actually going to help myself lay this out is to add a double pole, double throw switch and wire it up, and then I'm going to replace it with a header. Double pole, double throw. Let's see. It's a double pole, double throw relay. Do we have just a generic switch? Let's see. Switch. Toggle switch. I would like double pole, double throw. That's basically what I want. I don't really care what it actually is, because I'm not going to actually use this part. I'm just going to use it to help me think about how this circuit is wired. In fact, what I would probably do if I were clever is wire this up, save a copy or screenshot this and say, this is what the wiring looks like, but what's provided on the PCB is just a header. So let us, what is my... Let's just get these up and out of the way. Okay, so at this point, we can assume we've turned our power switch on. This line has 12 volts on it. And that 12 volt line is always going to go to the voltage regulator and to the relays. So I realize I haven't done relay power yet. But while I'm thinking of it, let me put in a little note here that this is always going to be relay power. Kenneth Finnegan says, I create line drawings of the schematic symbol that's off board if it's particularly important for certain functioning and understanding. Yeah, exactly. So like I would provide a drawing. To create like a line drawing like in the actual schematic itself, I think you're saying, Kenneth? I think that makes sense. So what I think I will do is just for the sake of understanding, I'm still going to use this little switch component as shorthand. But that is a good idea once I'm done with it to just take it away and recreate it with a drawing that's just lines. Okay, so really the end result of all this is it kind of says, yeah, line artwork that makes it look like a component. Yeah, exactly. So we'll implement that once the schematic is done. Let me step away for 30 seconds. I'm going to grab my cheat sheet here, which tells me how I actually laid out this circuit. I'm back. Okay, so here's the gist of it. So I need to basically switch in both the negative and positive lead of my secondary power source. So if I have 12 volts going into the first half of this switch, let's create a little text note for us that helps us remember which position of these switches is the if that's powered by single source configuration or which is the double source configuration. So I'm going to make it very verbose because we're going to get rid of this eventually. So we're calling it single FET power source. Let's say that's the upper position of these switches, and the lower position of these switches is the double FET power source. Oops, I created too many texts. Okay. Great. So let's put our goal out here, which is going to be to connect some power to our power rail, which we labeled earlier as $power. So let us name this net the same to link those up. Yep, power. Okay, and let's label that. Great. Okay, so ultimately we're going to be delivering either, I know I've been flopping around with numbers, but let's say 13.8 volts or 27.4 volts to this power line. So if I have a single FET power source, which basically means I want this power to power those FETs directly. Well, that's pretty straightforward. All I want is for that to be directly connected. And ultimately, what happens over here doesn't really matter in this configuration. Okay. So it's the position where these switches are flipped, where these are triggered, is actually the more interesting case. So let me illustrate here with a battery that has a nice battery symbol in it. Yeah, all right. So, oops. Battery. Let's just drop a whole battery right in the middle of things there. No, it's fine. I was hoping for one with more cells because it's an SLA, but again, I guess I'm deleting all this anyway. It doesn't really matter. Okay, so let us say that it's oriented in that direction. I'm gonna just move. Oops, I'm gonna just move. Shush. I'm gonna just move this over. Boop, boop, boop. Move that, and move that. Okay. So when we flip our double pole, double throw switch to double FET power source mode, let's say, so I'm going to flip this over, I'm going to connect this here. So in that case, I want this plus 12 volts, this positive line, to actually connect to the negative side of this other power supply or battery. And I want the positive side of that to connect to the other half of this switch, and then that connects to our power rail. Let's see, there must be a clearer way to draw this that doesn't have so many overlapping lines. I think the answer would be to... yeah, it's not super great. Let's see. How's that? That's all right. I'm not a huge fan. Okay, so just to recap, with the double pole double throw switch in the single FET power port position, this power line is connected straight through to the single, say, plus 12 volt power source up here, and is not connected to anything on this wire. This wire means nothing. If we were to flip both halves of this switch down, now this plus 12 volts is actually being sort of applied to the negative side of this power supply or battery. Then coming out the positive side of that power supply or battery, we go through here, we go to our power rail, and then this wire is not connected to anything on this switch, so that means nothing. So the difference between this power rail and ground would be the series combination of those two power supplies. Okay, so that is the intended wiring of all of this. Now I am going to represent all of that in a pin header. It's going to go great. Let's see. So we really only need a 2x5 header, but I'm going to introduce a 2x6, I think. Sorry, a 2x3 with 6 pins. So 2x3. Yeah, okay. 2x3. Great. I'm going to move these even further out of the way. So the real takeaway here is that, let's see, I don't think it would hurt anything for the, well, let's rotate this a little bit. I was thinking about numbering of all these pins, and I think keeping it consistent between our drawing and our pin header is not a bad idea. So in that case, here's the connections that we would need. So pin number 2 connects to my power line, my plus 12 volt input line. Pin number 1 connects to my power rail. So let's recreate our power rail over here. Yes. Make a little circle there just for interest's sake, and then, oops, we will label that. So pin 1 connects to our power rail. Pin 3 connects to the alternate power source. So I need another set of headers that is going to represent my secondary power source. So let me copy those. And actually, let me rearrange this just a little bit. That could be the theme of this layout project. Let me just rearrange this just a little bit. I'm just going to move things over. So this now is going to be, maybe I'll come up with a better name for it later, but let's call this 12 volt alt for alternate power supply, and we'll name this ground. Oh yeah, I can't name it the same thing. Well, we'll figure that out when we come to layout. So 12 volt alternate, let's see, the positive, oh, this also should not be ground. This is 12 volt alt minus, and this is 12 volt alt plus. I probably need a catchier name for those, but for the time being, that will do it. So pin 3 connects to the negative side of our pin here. Pin 4 connects to nothing. Pin 5 connects to the positive pin, and pin 6 is also connected to the power rail. Wow, 1 and 6 connect to the power rail. It's going to be just a little bit of a mess. I could do a second symbol out here, or I could try and tie it in there. I think this is what I'm going to do for now. It's not the most clean, but I've done worse. Okay. Kenneth Finnegan Boat's second symbol. Ooh. Dangling net names make schematics clearer. Yeah, that's fair. All right. So we're gonna do do this. We'll do so, and we'll label. Oh, and I need to name this then power. Yes. Okay. Yeah, like I say, I'm sure there is a cleaner way to indicate this kind of dangling net than just like me physically drawing a circle on the schematic. I'm sure there is a way. Somebody must know. But for the time being, that will make it work. All right, so all of this part of the schematic is not really part of the schematic, right? This was just for our to deduce things. So let us do a quick line drawing on the info layer of what's actually going on here. We'll just kind of duplicate this schematic in line art. Probably need to make this a little bit bigger. So now we are using a PCB layout program as Microsoft Paint. So we're really winning. All right, and then let's see. This goes to our little battery down here. Draw a little battery. We'll draw. That goes back into that switch. All right, well, it's not bad. It needs a bunch of labeling. All right, let's delete. This is not, I think, typical syntax, typical symbols for a double pole, double throw switch, but oh, a dotted line? Do I want a dotted line? Oof, come on. Welcome to my circuit layout speed run where we use an Autodesk product as Microsoft Paint. Here we go. All right, and then this is FET power. Let's see, we will do, that's plus 12 volts. And, all right, and so what I really need to add to this is the pin numbers for the switch that I've chosen, right? So 1, this is 2, this is 3. Wow, I really just winged these circles, huh? This is 4. This is 5. And this is 6. Wow. Got a little carried away there. Well, it's not an art podcast. It's not a podcast. It's not an art stream. It's a PCB layout stream. All right, so now, assuming I've captured all of this, I can delete it. 1, 2, 3, 4, 5, 6. Yeah, okay, so this is all going away. And this. So I'm sure if I were to pass this on to one of my assistant PCB layout designers and module designers. I'm sure they would have a thing or two to say about my art, but since ultimately, for the moment, the person assembling this is just me, I think that will be sufficient for determining what the hell I meant when I come back to this at some point in the future. Okay, so that's the alternate power switching arrangement, which I think is one of the more exciting parts about this portable lamp, because, you know, I guess sort of a little bit of backstory that I haven't given on this project. So the majority of my ham radio operating is portable and QRP, because I live in a first floor apartment in a 3-flat in the city of Chicago. We do have a little backyard, and I have put up a mast there portably. It takes temporarily on occasion, but not very much. So mostly I go to a park, I take a little QRP transceiver and a portable antenna, and I operate that way. And that is awesome. This is not to say anything against QRP operating. Like the other day, I was out testing a new antenna. It was super exciting. Like, I was bagging some of the 13 Colony special event stations at 5 watts with a temporary antenna. How cool. Like, just the rush of, you know, throwing out your call and somebody coming back while you're running off a little tiny battery. Awesome. But there are also times when you really would like to make that contact, even portably. So the sort of goal of this was for me to come up with some kind of small portable amplifier that could be battery powered, that at the moments I was like, you know, I really would like to, you know, I'm hearing somebody interesting, or I'd love to cut through the QSB for today or whatever, I could throw at a little bit more power and sort of just bag that contact when I needed to. I'm also thinking about, in October, the Illinois QSO party is coming up, when Illinois will be sort of the focal point of a contest for a change, and I would like to try running a pileup. Which on a portable antenna, I'm not going to do at 5 watts. It's just not going to happen. I mean, it might happen, but it seems unlikely. But if I could throw 50 watts at that, even with a portable vertical, I might stand a chance of generating a little bit of something and actually calling CQ for a while, which would be kind of a novelty for me. So won't that be exciting? All right, so we've done our power layout. We've done, here, let me name this. Just to be consistent, we'll call this switch 2. I guess we should look at relay switching. So this will be the point where I need to decide if I'm going to standardize on these little Fry's Electronics relays that I've chosen, or on some other relay solution. And I suppose, for the time being, I'm going to lay it out as if I'm using these Fry's relays, because they're not bad. They're 12 volts. They're relatively compact. They've taken all the RF I've thrown at them. I have a bunch of little single-pole, single-throw relays that I picked up for a song at a Hamfest, which is not really what I need, because I need the signal to be routed one way or the other and not just as a contact closure. So I guess what I'm leaning towards is using these relays in the layout for now, and then if I can work in some alternate footprints, then I will. So along those lines, I'm going to leave you looking at this schematic for just a second, while I go and get the little the little spec sheet that came with these relays, and we'll lay it out to match that. I threw that paper away. Oops. Well, that's going to make this more challenging. Well, I guess I have two options. One will be to either do a little Google-roo and see if Fry's Electronics happens to post that little schematic sheet online somewhere. And if not, then I will use my trusty calipers to actually measure the dimensions of this thing and do the layout based on that. But I have a relatively good feeling that I'm going to be able to find the little spec sheet for it. I mean, it wasn't a particularly in-depth spec sheet. I can also see if I can pull a part number off of this thing. Maybe that's the way to go. Survey says... it's part of the reason I didn't adhere these permanently to anything. All right, we've got a Good Sky RWSH1120. Let's see what we turn up. Oops. We've got a Good Sky RWSH1120. Or 112D? 112D. Oh, got me good. 112D? Really? 112D. Yeah. New glasses. First glasses. Very exciting. Day one. So far, it's going great. Data sheet. Data sheet. Aha! Great. So what I really just want is the footprint. There we go. Here, I'll tell you what, I'm going to move this off and we'll open up in Acrobat, and that will just be cleaner for everybody to look at. There we go. Okay. And let's get the Kenneth Finnegan window back up. There it is. All right, PCB layout. Yeah, so that is plenty of dimension work for us to be going on with, I think. Everything in millimeters, I assume. Looks like it. Yeah, I think it must be. All right, so let's make another part. Go into JGlib. We will while we're here, let's find a relay symbol that we can reuse. Guess I can do just this in the control panel. So, because I don't want to have to redraw that relay symbol if I can help it, just to make life easier on myself. Let's see. So I am looking for, so something like that would be fine as a symbol. I don't hate that. Octo, no, none of these are quite the thing. That is interesting. Oh, it's just a dual relay, but it's showing you both coils. That's kind of interesting. Let's go back to that first one. Oh gosh, come back. Yeah, how about one of these? That seems perfectly common. So again, so we're not using the package. I'm just going to reuse the symbol just to save myself some heartache. So that's the 4052. We're going to copy that to library. Boom. So I got the package and I have the symbol put in. Great. So let us do a new package, which is going to be for my part, which is the RWSH112D package. Yes. Alrighty, so let's do our grid. We're going to do our grid in millimeters because the part's in millimeters, and that will just be fine. Let's do 1 and 0.25. Do major grid is 1 millimeter, and my subgrid is 0.25 millimeters, just to make things really exciting. Okay, so let's go back to this here package. So total So the spacing between holes is specified. Let's see what it says about overall dimension. Dimension, less than 5 millimeters plus 0.2 millimeters, greater than 5 millimeters plus 3 millimeters, tolerance of PCB through hole plus 0.1 millimeters. Oh, okay, that's just our tolerance values. So that is just fine. So here's our dimensions. Total hole is 15.4 millimeters wide by 19 millimeters long. Great. We can do that. So we can put a line out here to 19 millimeters and 15 millimeters. Great. So that's the footprint of the device itself, or the package itself. And so now for the footprint of the through holes. So, So what is the spacing between the end of one of these things and the first pin? Looks like 2 millimeters to the first pin here. And then is there a dimension between this pin and this pin? Oh, yes, 2 millimeters there, but not a dimension to the first pin itself. Huh. Well, that's a little unfortunate. I mean, the pin spacing we can line up just fine with this diagram, but I would love it if it lined up with the dimensions of the package itself. I just don't see that there's any dimension that gives me what this dimension is. I get this dimension, and then I get this dimension, and then I get this dimension. Okay, great, never mind. So 3.4 millimeters from the end to this pair of pins. All right, well, good, I'm just slow. So let's go back into our drawing, and I'm gonna make my grid 0.1, so I can really take care of that. So, and I am going to go 3.5 millimeters, so 1, 2, 3, 16, 15.6. All right, so on that line will be our first pair of pins, which is these. And then we go 12.2 millimeters over to our next set of pins. So we're going from 15.6, oh, here comes more math on stream. We're going to 15.6 to, I'm going to 12.2 millimeters this away, so that would be 3.6, 3.4 from the other end. That'd be symmetrical, that'd be nice. So it would be 3.4. And now finally we go 2 millimeters over to go to our common pin there. So 3.4 go over 2, so 1.4 from the origin. Great. Okay, so that's those. So I'm actually going to take just a quick note of what those dimensions were 1.4 from the origin, 3.4, and 15.6. Okay. And then vertical spacing. Presumably this is centered. I don't know that. Yeah, so that's on center line. So and then we go 6 millimeters either way. So we said the total height of this thing, the total width of this thing was 15.4 millimeters. So center line is at 7.2. So then we go 6 millimeters off of that either way, and we get 1.2 and 13.2 millimeters. So here we come up from the origin 1.2 millimeters. There's that. And we come up 13.2. So there's that. And then we should do our center line as well. So if our total width was 15.4, we said, yeah? 15.4. So center line is at a 7 plus 0.7, so 7.7 millimeters. So there is, oops, there is that. there is that. Great. So that should be all of the dimensions that we need to start laying out our pins. I'm just going to real quick record what... did I goof this up? I hope not. These are 1.7, yeah? No? 1.2? So 1.2 plus 12... 1.2 plus 6 plus 6 plus 1.2 is 12 plus... I did goof this up. See, math on stream, not okay. That'd be 14.4. So really, these lines are not in the right place because I had these at 1.2 and they should be at 1.7. Okay. And then this one was at, let's see. Oh, except I think I may have done this upper one correctly. So this one would be at, let me see here, would be at 7.7 plus 6 plus, oh yeah, 13.7. Yeah, okay, and that's at, no, what did I goof up? Math on stream, 15.4 divided by 2. 7.7 is my center line, plus 6. 7.7 plus 6 should be at 13.7. Yeah, I goofed these both up. Now that doesn't look symmetrical at all. So I also have, so this should be at 1.7 though, yeah? Okay, so those are symmetrical. Oh, yeah, oh, because this is at 15 and not at 15.4. That would do it. So this whole shenanigans should be at 15.4, 15.4, 15.4. Okay, great. 0. Now I think we finally have the ability to put some holes in. So our hole sizes, so our contact pins are 3 millimeters, are 1.3 millimeters in diameter, and 1.3 millimeters in inches. .51, that seems plausible. Do I have a similarly sized hole? Let's see, I want... Oh, why are my pads so very big? Oh, these are in millimeters. Oh, well, there you go. 1.3. 1.3? 1.4? What's the smart... 0.051. Yes, 0.051, not 0.5. I got a half-inch hole for this relay. I'm going to put 100 amps through it. So I guess if the side of the hole is nominally 0.13 millimeters and the tolerance of the PCD through hole is 0.1 millimeter, I guess I should do, let's do 1.4 millimeter drills. So those are centered on the following coordinates. So these are at 3.4 and 1.7. Yes. Oops. No, 3.4 and 1.7. This one is at 13.7 and 3.4. Great. Oh, no, that's the wrong set of coordinates. Yeah, so this one is at 1.7, 15.6. Yeah. 13.7, 15.6, and then this one is at 7.7, 1.4. Great. And then the other set of holes is smaller. They are nominally 1 millimeter diameter. So let's do a 1.1 millimeter drill, and those go. That's what goes here. These coil pads. 13.7, 3.4. I guess I could zoom in and make my life a little easier. 3.7, 3.4. Okay. Cool. So there, except for this little wonky corner, is our relay symbol. So I am going to delete some of these helper lines. In fact, I'm going to delete all of them. And then, just because I can, I am going to reinstate a couple of them, just in case someone, aka me, wants to bodge in an alternate relay. They have the option. So I think normally closes the bottom when looked at. Let's see, is this a bottom view? Bottom view. So when we flip this over, the relay as looks down on from the top, this will be the normal connection. So I'm going to put the T place there, yeah. And then this is going to be. Shall we try and draw a coil? Oof. Rough. Well, I'm going to draw an inductor and ask forgiveness. Let's see. Draw a resistor. Coil has some resistance. It's true. So it could. I'm gonna be sassy about it. I'll be fine. I was gonna suggest we could also draw the like interturn capacitance of the coil, since it's not strictly a purely resistive load. But I think I'm actually just gonna. Wow, that's. I was gonna say we could live with it, but that just looks so bad. It just does not look good. I don't want that on my PCB. Well, I don't know that this is that much better. But it's something. Okay. So there's that. So that is the symbol. That is now going to become the package for one of these RWSH112D relays, which I have now apparently standardized on, or I will choose to do something else at a later date. Maybe do a dual footprint or something. Okay, so now let's look at our symbol that we were going to steal, which I guess is no, which was no, was you. Oh, they're separate symbols. Oh, that's quite clever. Okay, so we can do that. So I need a new device. This is going to be a what is this thing called? This is an RWSH112D. That's what this is called. This is an RWSH112D. New device, yes please. It's going to have one of those, and it's going to have one of those, and these are going to be. Now, do these have pins already in them? No, I'm going to need to add pins to this, aren't I? This is my first time doing one of these multi-symbol parts, which which is kind of exciting. But I don't know what best practices are as far as this is concerned. Well, all right. Well, let's. Well, I guess the trick will be let's just open up our device that we were stealing this from, and have a look at what's going on. So let's go back to our. That's our library screen. I want to go to here. Oh, so oh no. I pulled the whole relay in 4052. Okay, so let's save this for now, and let's open up this 4052 device and see what they've done. Okay, so this has connections, pin 1, pad 1, pin 1, 2. So do these individual symbols have pads in them? I guess that makes some sense. Let's go back into our RWSH112D. If I and I add, let's see, I'm gonna need to add a package here. So I'm gonna add our package that we just made. If I go to connect, oh great. So I do have my pads enumerated and my pins enumerated. I would love to be able to look at which pin is which on these symbols. I mean, presumably 2-1 and 2-2 are the halves of the relay, and I don't really care, but it's these pins that I want to be able to verify that I'm hooking them up correctly on the relay. Well, that is something I don't know how to do. I guess if I go into the symbol, the individual symbols, I should have pins, right? So I have pin 1 and pin 2 there as expected. And then if I go into the switch symbol, which is the one I really care about, P is the common, looks like O is the normally closed, and S is the normally open. I mean, I can roll with that. I have to think there's an easier way for me to look at this information, but that'll get me where we're going. So P, O, and S. So I'm going to go back into my package. Oops, not that one. I'm going to go back into my relay package, and I'm going to rename some of these. So I'm going to call this P. I'm going to call this O. I'm going to call this S. I'm going to call this C1 for coil 1 and C2 for coil 2. All right, go back into our device. And now when I connect, I should have coil 1, coil 2, O, P, and S. Great. Great. Well, that was relatively painless-ish. Let's add a description. A relay RWSH112D, which is, in this case, I don't know if these are all have a 12-volt coil, but this one does. All right, great. Well, that worked out pretty well. So now, if I go back into my schematic, and I go into my library, let's see, jglib, WSH, okay. Now why, if I drop one, and I drop the other, oh, how clever. Ooh, yeah, great. So, yeah, and the part numbers are the same, so they're the same part name, they're just two different symbols for it. Oh, well, that's great. I didn't know that was a thing, but that's very cool. Okay, so what I want is, I'm going to mirror this, yeah, because what I want, okay, so I'm also going to need a similar relay on the output side of things. So let's break that up. Move the RF out pin away. I'm going to, now here's an interesting, if I copy half of this part, will the other half come with it? No. So I need to create those separately. Interesting. So can I make this the other half of... Oh. It thinks it did. But where? Well, for the sake of expediency, I'm just going to manually add another one. All right, and there's those relays there. And I am going to flip this around. Yeah, great. So this is maybe not the best layout of this schematic, but oops, I am going to just set this up and make sure this is a net. Yeah, so that great. We'll tie that in just there, and then this will be the bypass line. So this is going to be kind of a messy way to draw it, but yeah, great. So when these relays are not triggered and there's no RF coming in here, all I want is for this RF in to go straight to the switch, go through the bypass line, and to RF out. So if the relay isn't powered, we're not seeing RF, the output and the input are connected. So I can receive through the amplifier, I can just turn the power off and I can choose not to receive, which is exactly what I want. Okay, well that's great. So now all I need to do is wire in these relays. Let me see here. Make sure everything is still kosher. Yeah, great. Okay, and sorry, you're seeing all of the little flickeries as I alt-tab between everything. Okay, so now I just want to wire up these relays in parallel. So and I will tie this. So this line here is going to be that relay power line that I established earlier. What did I call this net? This net is called 12 volts. So this is going to be 12 volts. And yes, they are connected. And this is great. So, great. So whenever this power switch is on, let me move this down to this other switch. So whenever there's 12 volts going to the system, there's 12 volts going to the 5-volt regulator, and there's 12 volts going to potentially power these relays. So there's 12 volts on this net here, and I probably will do a little extra bypassing of this as well. And then, because just for good measure, I am going to put a diode in reverse parallel across both of these relays, just so that when they turn off and you get that big power spike from the inductor releasing its magnetic energy back into the power line, it doesn't cause any problems down the line. Not that I think anything in this circuit would be fine. There'd be enough bypassing on that power line that it won't really be an issue. But I think this is not bad practice. So let's drop in our generic diode here, and we'll put one there, and we'll come back and clean that up at some later point, and we'll just make this clear that this is to be associated with each of these relays. And then we're gonna junction the bejesus out of this and of that. We have to do such a big junction check at the end of all this. Oops. Okay. So the next layout challenge I've given myself, and I'm just gonna be lazy about it, is that when I didn't really leave myself enough room for this RF switching section, so that's signal flow now. But so be it. Let's see, there was something else I meant to put in here. Oh, yeah, so the other thing I'm going to put in here, I would love to have an LED indicator of when the relays are switched on. It's super easy to hear the relays the moment when it's out in the open air, but I would love to have an indicator that that actually tells me that the relays are switched and that this line is being driven low, just as like a nice visual thing, especially if I've got headphones on or doing some operating or something. So I think what I'm going to do is put an LED between this plus 12 volt net and this net here, because this is being pulled to ground when this this transistor is being driven by the RF energy coming in. So I only worry, so I know a fair amount of the current is going to be flowing through the coils of these relays, but I hope there is enough, with a sufficiently, with the appropriate resistor, I think I can still get an LED to light up here. And if not, it's worth a try. That LED I'm going to leave as a pin header as well, just so I can mount that to the front panel. So what do I need? So I need a resistor, and I need a generic LED. I'll bet there is a library just called LED. If I'm lucky, there's a library called LED. Yeah, great. Give me a generic, just your good old-fashioned, nothing fancy about it. I really don't care what the symbol is. Oh, actually, you know what? I don't need an LED. I need a pin header. And then I'm going to draw an LED and remind people what it's supposed to be used for. So we'll do a 2x2 and 1x2. There we go. A 2-pin header. We're going to name it LED. And then we're going to get this wired up. So get that wired in there, and then we'll wire that there, and then we're going to give ourselves some info that this is meant to represent an LED. Let's see, I want that drawing mode. Great, there's my little sketch of an LED. That's not the worst. Okay. And 1K should be fine. So I want to say that these particular relays, let's see, nominal coil resistance is 400 ohms. So if I put two of them in parallel, nominal coil resistance is 200 ohms. So if I put a resistor in parallel with that wants to put, say, 20 milliamps through an LED with a forward voltage of, let's say, 2 volts. So let me think about what that would want to be. So I want, seat of my pants, so I have 10 volts to play with here. So essentially, and I want 20 milliamps to flow. So in isolation, 500 ohms. Oh, yeah, 500 ohms. Let's just label that. Let's just value that at 560 and call it a day. Let's value that down. Let's do it 1K. That should be fine. Yeah, it should be fine. We'll just standardize on that. So, all right, so now I've got my switching circuitry, I've got my LED indicator, I've got my relays wired up, I think. Oh, I didn't wire them very well, though, did I? Let's wire that one in there. Let's wire that one in there. Okay. So, let's recap everything that we've done today. So, here's the circuit. The RF input comes in here at about 5 watts out of a QRP transceiver. If there is no power, then this relay stays unchanged, and signal bypasses the amplifier, goes straight to RF out. Great, that's the easy part. If there is power, this relay can be actuated, and it's activated by this RF sense section, right, which is sampling the RF energy through a voltage divider. It's getting rectified, and then that is driving this transistor into conduction. That's allowing current to flow through these two 12-volt relays that we built the symbol for, as well as this indicator LED, which will be our basically our PTT LED, right? So that will cause this relay to actuate. So signal will flow through this 3 dB pi network attenuator, which is nominally 290 ohms in shunt. Ooh, these all need ground symbols. Man, these are just hanging resistors. See, this is essentially the equivalent of rubber duck debugging, right? Like, I'm just using all you nice folks out there in YouTube land as my excuse to troubleshoot this thing. All right, so going through this pi attenuator, these nominal values of 18 and 290, and a bunch of unpopulated area, so I can make up those with resistors in parallel if I so choose. So that signal then passes down, around, goes through this trifilar round transformer with its center tap is not actually the right word, but it's basically splitting this signal in two. Half of it is grounded, half of which is terminated with 100 ohms to ground. Through our DC blocking cap, we have our bias circuitry here, and we'll look at power when we come to the end of this thing. Those are driving the IRF 510s. Ooh, hey, here's another error. So, this was connected to the source there, and not to the drain. So that's going to ruin the symmetry of my schematic a little, but that will be just fine. All right, and then these also need to be grounded. So there's that, and there's that. Okay, so those are grounded, so tied directly to ground, and then the drains of those are hooked up to our power line here, and I promised we'll look at power at the end, which is well bypassed down here. Those are fed through this bifilar transformer that's wound on a T3743. Then we go to our output transformer, which in my case is two BN43202s, but in the future could be a BN437051 or similar. We built the package for that larger 7051, so we have plenty of room for a larger core later if we need it. And then this relay will also have been triggered by that RF sense section way back in the beginning, and will go out through another pin header out to a panel mount coax connector. And this reminds me, I actually need another ground point out here to tie that into. Great. So that will be grounded. Let me just move this ground over here because I can. Great. All right, and then just look at power real quick. So we have two power switches in the back. We have a 12 volts nominal source coming in here. We have a hard power switch which just cuts that off. So this is the main on-off switch for the amplifier. Ignoring all this for a sec, that 12 volts will just pass right down this power line. It goes to a 5 volt 7805 regulator, which is providing 5 volts for the bias circuitry and 12 volts for the relay power. Now, to the power line for the drains of the FETs, so this power line down here, which was feeding this transformer, which is feeding those FETs, we have this secondary double pull, double throw switch. So if it is in the single power position, power comes in here on the 12-volt line and then just goes straight out to those FET drains. So we're powering both like the relays and the FETs with the same power source. However, if we have a secondary 12-volt nominal source, we can switch to this other position, which puts this battery or power supply or whatever in series with our initial power supply before powering those FETs. So this is an option to go up to plus 26, 27 volts on those FETs. So that, modulo some final error checking, and that I'm sure couldn't hurt anything, and looking for places that I've missed junctions on, that essentially is the circuit for our QRP 50 watt, 60 watt output amplifier, which is essentially this. That's pretty good. So finally, we can generate a board. Bum, 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 bum. Oh my goodness. Oh, this is going to be quite a layout challenge and quite a layout joy. And we still have some things to think about with this layout, including, you know, is this really the form factor for those IRF 510s that we want? We're still thinking about what our heatsink options are. Still thinking about what this transformer really wants to look like. We've got a few things. Do we want to have an alternate package for this relay? I just don't know. But for the time being, I think that is going to wrap it up for tonight's stream. I don't think I have another several hours in me to lay out this board in full. But thank you to those of you who have been watching this stream throughout. Thanks to all of you who might be watching this in the future, and maybe this was useful. Maybe some of the questions I had were some of the questions that you had as well. I'll have to come back at some later point and hopefully do a layout of this on stream. But if not, I'll be sure to show off this project at another point. Thank you to KWF for keeping things calm in the chat. I always appreciate it, and for all of the data sheets that got posted along the way. And for the time being, I'm just going to say 73, and we'll catch you on this project next time. Bye, y'all.